Learning objectives. In this chapter, the user would learn the following in detail: memory management, logical versus physical address space, swapping, contiguous allocation, paging, segmentation, segmentation with paging. Virtual memory, demand paging, performance of demand paging, page replacement algorithms, thrashing, demand segmentation, file. System interface, access methods, directory structure, protection, consistency semantics, partitions, simple volumes, shadow volumes, virtual disks, BitLocker. File system implementation, file system structure, allocation methods, free space management, directory. Implementation, efficiency and performance, recovery. Access methods. Files store information. When it is used, this information must be accessed and read into computer memory. The information in the file can be accessed in several ways. Some systems provide only one access method of files, while others support many access methods, and choosing the right one for a particular application is a major design problem. Sequential access. The simplest access method is a sequential access. Information in the file is processed in order, one record after the other. This mode of access is by far the most common. For example, editors and compilers usually access files in this fashion. Reads and writes make up the bulk of the operations on a file. A read operation, read next function, reads the next portion of the file and automatically advances a file pointer which tracks the input-output location. Similarly, the write operation, write next function, appends to the end of the file and advances to the end of the newly written material, the new end of file. Such a file can be reset to the beginning, and on some systems, a program may be able to skip forward or backward n records for some integer n, perhaps only for n equals 1. Sequential access, which is depicted in figure below, is based on a tape model of a file and works as well on sequential access devices as it does on random access ones. Direct access. Another method is direct access or relative access. Here, a file is made up of fixed-length logical records that allow programs to read and write records rapidly in no particular order. The direct access method is based on a disk model of a file, since disks allow random access to any file block. For direct access, the file is viewed as a numbered sequence of blocks or records. Thus, we may read block 14, then read block 53, and then write block 7. There are no restrictions on the order of reading or writing for a direct access. Direct access files are of great use for immediate access to large amounts of information. Databases are often of this type. When a query concerning a particular subject arrives, we compute which block contains the answer and then read that block directly to provide the desired information. As a simple example, on an airline reservation system, we might store all the information about a particular flight, for example, flight 713, in the block identified by the flight number. Thus, the number of available seats for flight 713 is stored in block 713 of the reservation file. To store information about a larger set, such as people, we might compute a hash function on the people's names or search a small in-memory index to determine a block to read and search. For the direct access method, the file operations must be modified to include the block number as a parameter. Thus, we have read n function, where n is the block number, rather than read next function, and write n function rather than write next function. An alternative approach is to retain read next function and write next function as with sequential access, and to add an operation position file n, where n is the block number. Then, to effect a read n function, we would position the file n and then read next function. The block number provided by the user to the operating system is normally a relative block number. A relative block number is an index relative to the beginning of the file. Thus, the first relative block of the file is 0, the next is 1, and so on, even though the absolute disk address may be 14,703 for the first block and 3,192 for the second. The use of relative block numbers allows the operating system to decide where the file should be placed, called the allocation problem, and helps to prevent the user from accessing portions of the file system that may not be part of a file. Some systems start their relative block numbers at 0, others start at 1. How then does the system satisfy a request for record n in a file? Assuming we have a logical record length L, the request for record n is turned into an input-output request for L bytes starting at location L, with n variable within the file, assuming the first record is n equals to 0. Since logical records are of a fixed size, it is also easy to read, write, or delete a record. Not all operating systems support both sequential and direct access for files. Some systems allow only sequential file access, while others allow only direct access. Some systems require that a file be defined as sequential or direct when it is created. Such a file can be accessed only in a manner consistent with its declaration. We can easily simulate sequential access on a direct access file by simply keeping a variable CP that defines our current position as shown in figure below. Simulating a direct access file on a sequential access file, however, is extremely inefficient and clumsy. Other access methods. Other access methods can be built on top of a direct access method. These methods generally involve the construction of an index for the file. The index, like an index in the back of a book, contains pointers to the various blocks. To find a record in the file, we first search the index and then use the pointer to access the file directly and to find the desired record. For example, a retail price file might list the universal product codes, UPCs, for items with the associated prices. Each record consists of a 10-digit UPC and a 6-digit price for a 16-byte record. If our disk has 1024 bytes per block, we can store 64 records per block. A file of 120,000 records would occupy about 2,000 blocks, 2 million bytes. By keeping the file sorted by UPC, we can define an index consisting of the first UPC in each block. This index would have 2,000 entries of 10 digits each, or 20,000 bytes, and thus could be kept in memory. To find the price of a particular item, we can make a binary search of the index. From this search, we learn exactly which block contains the desired record and access that block. This structure allows us to search a large file doing little input-output. With large files, the index file itself may become too large to be kept in memory. One solution is to create an index for the index file. The primary index file contains pointers to secondary index files which point to the actual data items. For example, IBM's Indexed Sequential Access method, ISAM, uses a small master index that points to disk blocks of a secondary index. The secondary index blocks point to the actual file blocks. The file is kept sorted on a defined key. To find a particular item, we first make a binary search of the master index, which provides the block number of the secondary index. This block is read in, and again a binary search is used to find the block containing the desired record. Finally, this block is searched sequentially. In this way, any record can be located from its key by at most 2 direct access reads. Figure below shows a similar situation as implemented by VMS Index and relative files. Allocation methods. The direct access nature of disks gives us flexibility in the implementation of files. In almost every case, many files are stored on the same disk. The main problem is how to allocate space to these files so that disk space is utilized effectively and files can be accessed quickly. 3 major methods of allocating disk space are in wide use: contiguous, linked, and indexed. Each method has advantages and disadvantages. Although some systems support all 3, it is more common for a system to use one method for all files within a file system type. Contiguous allocation. Contiguous allocation requires that each file occupy a set of contiguous blocks on the disk. Disk addresses define a linear ordering on the disk. With this ordering, assuming that only one job is accessing the disk, accessing block B plus 1 after block B normally requires no head movement. When head movement is needed from the last sector of one cylinder to the first sector of the next cylinder, the head need only move from one track to the next. Thus, the number of disk seeks required for accessing contiguously allocated files is minimal, as is seek time when a seek is finally needed. Contiguous allocation of a file is defined by the disk address and length in block units of the first block. If the file is n blocks long and starts at location B, then it occupies blocks B, B plus 1, B plus 2, so on till B plus n minus 1. The directory entry for each file indicates the address of the starting block and the length of the area allocated for this file. Figure shows contiguous allocation. Accessing a file that has been allocated contiguously is easy. For sequential access, the file system remembers the disk address of the last block referenced and, when necessary, reads the next block. For direct access to block I of a file that starts at block B, we can immediately access block B plus I. Thus, both sequential and direct access can be supported by contiguous allocation. Contiguous allocation has some problems, however. One difficulty is finding space for a new file. The system chosen to manage free space determines how this task is accomplished. These management systems. Any management system can be used, but some are slower than others. The contiguous allocation problem can be seen as a particular application of the general dynamic storage allocation problem, which involves how to satisfy a request of size n from a list of freeholds. First fit and best fit are the most common strategies used to select a freehold from the set of available holds. Simulations have shown that both first fit and best fit are more efficient than worst fit in terms of both time and storage utilization. Neither first fit nor best fit is clearly best in terms of storage utilization, but first fit is generally faster. All these algorithms suffer from the problem of external fragmentation. As files are allocated and deleted, the free disk space is broken into little pieces. External fragmentation exists whenever free space is broken into chunks. It becomes a problem when the largest contiguous chunk is insufficient for a request. Storage is fragmented into a number of holes, none of which is large enough to store the data. Depending on the total amount of disk storage and the average file size, external fragmentation may be a minor or a major problem. One strategy for preventing loss of significant amounts of disk space to external fragmentation is to copy an entire file system onto another disk. The original disk is then freed completely, creating one large contiguous free space. We then copy the files back onto the original disk by allocating contiguous space from this one large hole. This scheme effectively compacts all free space into one contiguous space, solving the fragmentation problem. The cost of this compaction is time, however, and the cost can be particularly high for large hard disks. Compacting these disks may take hours and may be necessary on a weekly basis. Some systems require that this function be done offline with the file system unmounted. During this downtime, normal system operation generally cannot be permitted, so such compaction is avoided at all costs on production machines. Most modern systems that need defragmentation can perform it online during normal system operations, but the performance penalty can be substantial. Another problem with contiguous allocation is determining how much space is needed for a file. When the file is created, the total amount of space it will need must be found and allocated. How does the creator, program, or person know the size of the file to be created? In some cases, this determination may be fairly simple, copying an existing file, for example. In general, however, the size of an output file may be difficult to estimate. If we allocate too little space to a file, we may find that the file cannot be extended. Especially with the best fit allocation strategy, the space on both sides of the file may be in use. Hence, we cannot make the file larger in place. Two possibilities then exist. First, the user program can be terminated with an appropriate error message. The user must then allocate more space and run the program again. These repeated runs may be costly. To prevent them, the user will normally overestimate the amount of space needed, resulting in considerable wasted space. The other possibility is to find a larger hole, copy the contents of the file to the new space, and release the previous space. This series of actions can be repeated as long as space exists, although it can be time-consuming. The user need never be informed explicitly about what is happening, however. The system continues despite the problem, although more and more slowly. Even if the total amount of space needed for a file is known in advance, pre-allocation may be inefficient. A file that will grow slowly over a long period, months or years, must be allocated enough space for its final size, even though much of that space will be unused for a long time. The file therefore has a large amount of internal fragmentation. To minimize these drawbacks, some operating systems use a modified contiguous allocation scheme. Here, a contiguous chunk of space is allocated initially. Then, if that amount proves not to be large enough, another chunk of contiguous space known as an extent is added. The location of a file's block is then recorded as a location and a block count plus a link to the first block of the next extent. On some systems, the owner of the file can set the extent size, but this setting results in inefficiencies if the owner is incorrect. Internal fragmentation can still be a problem if the extents are too large, and external fragmentation can become a problem as extents of varying sizes are allocated and delocated. The commercial Veritas file system uses extents to optimize performance. Veritas is a high-performance replacement for the standard Unix UFS. Linked allocation. Linked allocation solves all problems of contiguous allocation. With linked allocation, each file is a linked list of disk blocks. The disk blocks may be scattered anywhere on the disk. The directory contains a pointer to the first and last blocks of the file. For example, a file of 5 blocks might start at block 9 and continue at block 16, then block 1, then block 10, and finally block 25. Refer to figure below. Each block contains a pointer to the next block. These pointers are not made available to the user. Thus, if each block is 512 bytes in size and a disk address, the pointer requires 4 bytes, then the user sees blocks of 508 bytes. To create a new file, we simply create a new entry in the directory. With linked allocation, each directory entry has a pointer to the first disk block of the file. The pointer is initialized to null, the end of the list pointer value, to signify an empty file. The size field is also set to 0. A write to the file causes the free space management system to find a free block, and this new block is written to and is linked to the end of the file. To read a file, we simply read blocks by following the pointers from block to block. There is no external fragmentation with linked allocation, and any free block on the free space list can be used to satisfy a request. The size of a file need not be declared when the file is created. A file can continue to grow as long as free blocks are available. Consequently, it is never necessary to compact disk space. Linked allocation does have disadvantages, however. The major problem is that it can be used effectively only for sequential access files. To find the ith block of a file, we must start at the beginning of that file and follow the pointers until we get to the ith block. Each access to a pointer requires a disk read and some requires a disk seek. Consequently, it is inefficient to support a direct access capability for linked allocation files. Another disadvantage is the space required for the pointers. If a pointer requires 4 bytes out of a 512 byte block, then 0.78% of the disk is being used for pointers rather than for information. Each file requires slightly more space than it would otherwise. The usual solution to this problem is to collect blocks into multiples, called clusters, and to allocate clusters rather than blocks. For instance, the file system may define a cluster as 4 blocks and operate on the disk only in cluster units. Pointers then use a much smaller percentage of the file's disk space. This method allows the logical to physical block mapping to remain simple but improves disk throughput because fewer disk head seeks are required, and decreases the space needed for block allocation and free list management. The cost of this approach is an increase in internal fragmentation because more space is wasted when a cluster is partially full than when a block is partially full. Clusters can be used to improve the disk access time for many other algorithms as well, so they are used in most file systems. Yet another problem of linked allocation is reliability. Recall that the files are linked together by pointers scattered all over the disk, and consider what would happen if a pointer were lost or damaged. A bug in the operating system software or a disk hardware failure might result in picking up the wrong pointer. This error could in turn result in linking into the free space list or into another file. One partial solution is to use doubly linked lists, and another is to store the file name and relative block number in each block. However, these schemes require even more overhead for each file. An important variation on linked allocation is the use of a file allocation table (FAT). This simple but efficient method of disk space allocation was used by the MS-DOS operating system. A section of disk at the beginning of each volume is set aside to contain the table. The table has one entry for each disk block and is indexed by block number. The FAT is used in much the same way as a linked list. The directory entry contains the block number of the first block of the file. The table entry indexed by that block number contains the block number of the next block in the file. This chain continues until it reaches the last block, which has a special end-of-file value as the table entry. An unused block is indicated by a table value of 0. Allocating a new block to a file is a simple matter of finding the first 0-valued table entry and replacing the previous end-of-file value with the address of the new block. The 0 is then replaced with the end-of-file value. An illustrative example is the FAT structure shown in figure below, file allocation table for a file consisting of disk blocks 217, 618 and 339. The FAT allocation scheme can result in a significant number of disk head seeks unless the FAT is cached. The disk head must move to the start of the volume to read the FAT and find the location of the block in question, then move to the location of the block itself. In the worst case, both moves occur for each of the blocks. A benefit is that random access time is improved because the disk head can find the location of any block by reading the information in the FAT. Indexed allocation. Linked allocation solves the external fragmentation and size declaration problems of contiguous allocation. However, in the absence of a FAT, linked allocation cannot support efficient direct access since the pointers to the blocks are scattered with the blocks themselves all over the disk and must be retrieved in order. Indexed allocation solves this problem by bringing all the pointers together into one location, the index block. Each file has its own index block, which is an array of disk block addresses. The ith entry in the index block points to the ith block of the file. The directory contains the address of the index block, figure below. To find and read the ith block, we use the pointer in the ith index block entry. This scheme is similar to the paging scheme. When the file is created, all pointers in the index block are set to null. When the ith block is first written, a block is obtained from the free space manager and its address is put in the ith index block entry. Indexed allocation supports direct access without suffering from external fragmentation because any free block on the disk can satisfy a request for more space. Indexed allocation does suffer from wasted space, however. The pointer overhead of the index block is generally greater than the pointer overhead of linked allocation. Consider a common case in which we have a file of only 1 or 2 blocks. With linked allocation, we lose the space of only 1 pointer per block. With indexed allocation, an entire index block must be allocated even if only 1 or 2 pointers will be non-null. This point raises the question of how large the index block should be. Every file must have an index block, so we want the index block to be as small as possible. If the index block is too small, however, it will not be able to hold enough pointers for a large file, and a mechanism will have to be available to deal with this issue. Mechanisms for this purpose include the following. Linked scheme. An index block is normally one disk block. Thus, it can be read and written directly by itself. To allow for large files, we can link together several index blocks. For example, an index block might contain a small header giving the name of the file and a set of the first 100 disk block addresses. The next address, the last word in the index block, is null for a small file or is a pointer to another index block for a large file. Multi-level index. A variant of linked representation uses a first-level index block to point to a set of second-level index blocks, which in turn point to the file blocks. To access a block, the operating system uses the first-level index to find a second-level index block and then uses that block to find the desired data block. This approach could be continued to a third or fourth level depending on the desired maximum file size. With 4096 byte blocks, we could store 1024 4-byte pointers in an index block. Two levels of indexes allow 1,048,576 data blocks and a file size of up to 4 GB. Combined scheme. Another alternative used in Unix-based file systems is to keep the first, say, 15 pointers of the index block in the file's inode. The first 12 of these pointers point to direct blocks, that is, they contain addresses of blocks that contain data of the file. Thus, the data for small files of no more than 12 blocks do not need a separate index block. If the block size is 4 KB, then up to 48 KB of data can be accessed directly. The next 3 pointers point to indirect blocks. The first points to a single indirect block, which is an index block containing not data, but the addresses of blocks that do contain data. The second points to a double indirect block, which contains the address of a block that contains the addresses of blocks that contain pointers to the actual data blocks. The last pointer contains the address of a triple indirect block. A Unix inode is shown in figure. Under this method, the number of blocks that can be allocated to a file exceeds the amount of space addressable by the 4-byte file pointers used by many operating systems. A 32-bit file pointer reaches only 232 bytes or 4 GB. Many Unix and Linux implementations now support 64-bit file pointers, which allow files and file systems to be several XB bytes in size. The ZFS file system supports 128-bit file pointers. Indexed allocation schemes suffer from some of the same performance problems as does linked allocation. Specifically, the index blocks can be cached in memory, but the data blocks may be spread all over a volume. Performance. The allocation methods that we have discussed vary in their storage efficiency and data block access times. Both are important criteria in selecting the proper method or methods for an operating system to implement. Before selecting an allocation method, we need to determine how the systems will be used. A system with mostly sequential access should not use the same method as a system with mostly random access. For any type of access, contiguous allocation requires only one access to get a disk block. Since we can easily keep the initial address of the file in memory, we can calculate immediately the disk address of the ith block or the next block and read it directly. For linked allocation, we can also keep the address of the next block in memory and read it directly. This method is fine for sequential access. For direct access, however, an access to the ith block might require I-disk reads. This problem indicates why linked allocation should not be used for an application requiring direct access. As a result, some systems support direct access files by using contiguous allocation and sequential access files by using linked allocation. For these systems, the type of access to be made must be declared when the file is created. A file created for sequential access will be linked and cannot be used for direct access. A file created for direct access will be contiguous and can support both direct access and sequential access, but its maximum length must be declared when it is created. In this case, the operating system must have appropriate data structures and algorithms to support both allocation methods. Files can be converted from one type to another by the creation of a new file of the desired type into which the contents of the old file are copied. The old file may then be deleted and the new file renamed. Indexed allocation is more complex. If the index block is already in memory, then the access can be made directly. However, keeping the index block in memory requires considerable space. If this memory space is not available, then we may have to read first the index block and then the desired data block. For a two-level index, two index block reads might be necessary. For an extremely large file, Accessing a block near the end of the file would require reading in all the index blocks before the needed data block finally could be read. Thus, the performance of indexed allocation depends on the index structure, on the size of the file, and on the position of the block desired. Some systems combine contiguous allocation with indexed allocation by using contiguous allocation for small files up to 3 or 4 blocks and automatically switching to an indexed allocation if the file grows large. Since most files are small and contiguous allocation is efficient for small files, average performance can be quite good. Many other optimizations are in use. Given the disparity between CPU speed and disk speed, it is not unreasonable to add thousands of extra instructions to the operating system to save just a few disk head movements. Furthermore, this disparity is increasing over time to the point where hundreds of thousands of instructions could reasonably be used to optimize head movements. BitLocker. In contrast, NTFS uses ACLS to control access to individual files and supports implicit encryption of individual files or entire volumes using Windows BitLocker feature. Windows uses encryption as part of common protocols such as those used to communicate securely with websites. Encryption is also used to protect user files stored on disk from prying eyes. Windows 7 allows users to easily encrypt virtually a whole disk as well as removable storage devices such as USB flash drives with a feature called BitLocker. If a computer with an encrypted disk is stolen, the thieves will need very sophisticated technology such as an electron microscope to gain access to any of the computer's files. Windows uses digital signatures to sign operating system binaries so it can verify that the files were produced by Microsoft or another known company. In some editions of Windows, a code integrity module is activated at boot to ensure that all the loaded modules in the kernel have valid signatures, assuring that they have not been tampered with by an offline attack. Consistency semantics. Consistency semantics represent an important criterion for evaluating any file system that supports file sharing. These semantics specify how multiple users of a system are to access a shared file simultaneously. In particular, they specify when modifications of data by one user will be observable by other users. These semantics are typically implemented as code with the file system. Consistency semantics are directly related to the process synchronization algorithms. However, the complex algorithms of that chapter tend not to be implemented in the case of file input-output because of the great latencies and slow transfer rates of disks and networks. For example, performing an atomic transaction to a remote disk could involve several network communications, several disk reads and writes, or both. Systems that attempt such a full set of functionalities tend to perform poorly. A successful implementation of complex sharing semantics can be found in the Andrew file system. For the following discussion, we assume that a series of file accesses, that is, reads and writes, attempted by a user to the same file is always enclosed between the open function and close function operations. The series of accesses between the open function and close function operations makes up a file session. To illustrate the concept, we sketch several prominent examples of consistency semantics. Unix semantics. The Unix file system uses the following consistency semantics. Writes to an open file by a user are visible immediately to other users who have this open file. One mode of sharing allows users to share the pointer of current location into the file. Thus, the advancing of the pointer by one user affects all sharing users. Here, a file has a single image that interleaves all accesses regardless of their origin. In the Unix semantics, a file is associated with a single physical image that is accessed as an exclusive resource. Contention for this single image causes delays in user processes. Session semantics. The Andrew file system, OpenAFS, uses the following consistency semantics. Writes to an open file by a user are not visible immediately to other users that have the same file open. Once a file is closed, the changes made to it are visible only in sessions starting later. Already open instances of the file do not reflect these changes. According to these semantics, a file may be associated temporarily with several, possibly different, images at the same time. Consequently, multiple users are allowed to perform both read and write accesses concurrently on their images of the file without delay. Almost no constraints are enforced on scheduling accesses. Immutable shared files semantics. A unique approach is that of immutable shared files. Once a file is declared as shared by its creator, it cannot be modified. An immutable file has two key priorities: its name may not be reused, and its contents may not be altered. Thus, the name of an immutable file signifies that the contents of the file are fixed. The implementation of these semantics in a distributed system is simple because the sharing is disciplined, read-only. Contiguous allocation. The main memory must accommodate both the operating system and the various user processes. We therefore need to allocate main memory in the most efficient way possible. Contiguous allocation is also known as contiguous memory allocation. This section explains one early method, contiguous memory allocation. The memory is usually divided into two partitions, one for the resident operating system and one for the user processes. We can place the operating system in either low memory or high memory. The major factor affecting this decision is the location of the interrupt vector. Since the interrupt vector is often in low memory, programmers usually place the operating system in low memory as well. Thus, in this text, we discuss only the situation in which the operating system resides in low memory. The development of the other situation is similar. We usually want several user processes to reside in memory at the same time. We therefore need to consider how to allocate available memory to the processes that are in the input queue waiting to be brought into memory. In contiguous memory allocation, each process is contained in a single section of memory that is contiguous to the section containing the next process. Memory protection. Before discussing memory allocation further, we must discuss the issue of memory protection. We can prevent a process from accessing memory it does not own by combining two ideas previously discussed. If we have a system with a relocation register together with a limit register, we accomplish our goal. The relocation register contains the value of the smallest physical address. The limit register contains the range of logical addresses. For example, relocation equals to 100040 and limit equals to 74600. Each logical address must fall within the range specified by the limit register. The MMU maps the logical address dynamically by adding the value in the relocation register. This mapped address is sent to memory. Figure below. When the CPU scheduler selects a process for execution, the dispatcher loads the relocation and limit registers with the correct values as part of the context switch. Because every address generated by a CPU is checked against these registers, we can protect both the operating system and the other users' programs and data from being modified by this running process. The relocation register scheme provides an effective way to allow the operating system's size to change dynamically. This flexibility is desirable in many situations. For example, the operating system contains code and buffer space for device drivers. If a device driver or other operating system service is not commonly used, we do not want to keep the code and data in memory, as we might be able to use that space for other purposes. Such code is sometimes called transient operating system code. It comes and goes as needed. Thus, using this code changes the size of the operating system during program execution. Memory allocation. Now we are ready to turn to memory allocation. One of the simplest methods for allocating memory is to divide memory into several fixed-sized partitions. Each partition may contain exactly one process. Thus, the degree of multiprogramming is bound by the number of partitions. In this multiple partition method, when a partition is free, a process is selected from the input queue and is loaded into the free partition. When the process terminates, the partition becomes available for another process. This method was originally used by the IBM OS 360 operating system called MFT, but is no longer in use. The method described next is a generalization of the fixed partition scheme called MVT. It is used primarily in batch environments. Many of the ideas presented here are also applicable to a time-sharing environment in which pure segmentation is used for memory management. In the variable partition scheme, the operating system keeps a table indicating which parts of memory are available and which are occupied. Initially, all memory is available for user processes and is considered one large block of available memory, a whole. Eventually, as you will see, memory contains a set of holes of various sizes. As processes enter the system, they are put into an input queue. The operating system takes into account the memory requirements of each process and the amount of available memory space in determining which processes are allocated memory. When a process is allocated space, it is loaded into memory and it can then compete for CPU time. When a process terminates, it releases its memory, which the operating system may then fill with another process from the input queue. At any given time then, we have a list of available block sizes and an input queue. The operating system can order the input queue according to a scheduling algorithm. Memory is allocated to processes until, finally, the memory requirements of the next process cannot be satisfied, that is, no available block of memory or hole is large enough to hold that process. The operating system can then wait until a large enough block is available, or it can skip down the input queue to see whether the smaller memory requirements of some other process can be met. In general, as mentioned, the memory blocks available comprise a set of holes of various sizes scattered throughout memory. When a process arrives and needs memory, the system searches the set for a hole that is large enough for this process. If the hole is too large, it is split into two parts. One part is allocated to the arriving process, the other is returned to the set of holes. When a process terminates, it releases its block of memory, which is then placed back in the set of holes. If the new hole is adjacent to other holes, these adjacent holes are merged to form one larger hole. At this point, the system may need to check whether there are processes waiting for memory and whether this newly freed and recombined memory could satisfy the demands of any of these waiting processes. This procedure is a particular instance of the general dynamic storage allocation problem, which concerns how to satisfy a request of size n from a list of free holes. There are many solutions to this problem. The first fit, best fit, and worst fit strategies are the ones most commonly used to select a free hole from the set of available holes. First fit. Allocate the first hole that is big enough. Searching can start either at the beginning of the set of holes or at the location where the previous first fit search ended. We can stop searching as soon as we find a free hole that is large enough. Best fit. Allocate the smallest hole that is big enough. We must search the entire list unless the list is ordered by size. This strategy produces the smallest leftover hole. Worst fit. Allocate the largest hole. Again, we must search the entire list unless it is sorted by size. This strategy produces the largest leftover hole, which may be more useful than the smaller leftover hole from a best fit approach. Simulations have shown that both first fit and best fit are better than worst fit in terms of decreasing time and storage utilization. Neither first fit nor best fit is clearly better than the other in terms of storage utilization, but first fit is generally faster. Fragmentation. Both the first fit and best fit strategies for memory allocation suffer from external fragmentation. As processes are loaded and removed from memory, the free memory space is broken into little pieces. External fragmentation exists when there is enough total memory space to satisfy a request, but the available spaces are not contiguous. Storage is fragmented into a large number of small holes. This fragmentation problem can be severe. In the worst case, we could have a block of free or wasted memory between every two processes. If all these small pieces of memory were in one big free block instead, we might be able to run several more processes. Whether we are using the first fit or best fit strategy can affect the amount of fragmentation. First fit is better for some systems, whereas best fit is better for others. Another factor is which end of a free block is allocated, which is the leftover piece, the one on the top or the one on the bottom. No matter which algorithm is used, however, external fragmentation will be a problem. Depending on the total amount of memory storage and the average process size, external fragmentation may be a minor or a major problem. Statistical analysis of first fit, for instance, reveals that even with some optimization given n allocated blocks, another 0.5 n blocks will be lost to fragmentation. That is, 1/3 of memory may be unusable. This property is known as the 50% rule. Memory fragmentation can be internal as well as external. Consider a multiple partition allocation scheme with a whole of 18,464 bytes. Suppose that the next process requires 18,462 bytes. If we allocate exactly the requested block, we are left with a whole of 2 bytes. The overhead to keep track of this whole will be substantially larger than the whole itself. The general approach to avoiding this problem is to break the physical memory into fixed-sized blocks and allocate memory in units based on block size. With this approach, the memory allocated to a process may be slightly larger than the requested memory. The difference between these two numbers is internal fragmentation, unused memory that is internal to a partition. One solution to the problem of external fragmentation is compaction. The goal is to shuffle the memory contents so as to place all free memory together in one large block. Compaction is not always possible, however. If relocation is static and is done at assembly or load time, compaction cannot be done. It is possible only if relocation is dynamic and is done at execution time. If addresses are relocated dynamically, relocation requires only moving the program and data and then changing the base register to reflect the new base address. When compaction is possible, we must determine its cost. The simplest compaction algorithm is to move all processes toward one end of memory. All holes move in the other direction, producing one large hole of available memory. This scheme can be expensive. Another possible solution to the external fragmentation problem is to permit the logical address space of the processes to be non-contiguous, thus allowing a process to be allocated physical memory wherever such memory is available. Two complementary techniques achieve this solution: segmentation and paging. These techniques can also be combined. Fragmentation is a general problem in computing that can occur wherever we must manage blocks of data. Demand paging. Consider how an executable program might be loaded from disk into memory. One option to load the entire program in physical memory at program execution time. However, a problem with this approach is that we may not initially need the entire program in memory. Suppose a program starts with a list of available options from which the user is to select. Loading the entire program into memory results in loading the executable code for all options, regardless of whether or not an option is ultimately selected by the user. An alternative strategy is to load pages only as they are needed. This technique is known as demand paging and is commonly used in virtual memory systems. With demand paged virtual memory, pages are loaded only when they are demanded during program execution. Pages that are never accessed are thus never loaded into physical memory. A demand paging system is similar to a paging system with swapping. Figure below transfer of page memory to contiguous disk space, where processes reside in secondary memory, usually a disk. When we want to execute a process, we swap it into memory. Rather than swapping the entire process into memory, though, we use a lazy swapper. A lazy swapper never swaps a page into memory unless that page will be needed. In the context of a demand paging system, use of the term swapper is technically incorrect. A swapper manipulates entire processes, whereas a pager is concerned with the individual pages of a process. We thus use pager rather than swapper in connection with demand paging. Basic concepts. When a process is to be swapped in, the pager guesses which pages will be used before the process is swapped out again. Instead of swapping in a whole process, the pager brings only those pages into memory. Thus, it avoids reading into memory pages that will not be used anyway, decreasing the swap time and the amount of physical memory needed. With this scheme, we need some form of hardware support to distinguish between the pages that are in memory and the pages that are on the disk. The valid-invalid bit scheme can be used for this purpose. This time, however, when this bit is set to valid, the associated page is both legal and in memory. If the bit is set to invalid, the page is not valid, that is, not in the logical address space of the process, or is valid but is currently on the disk. The page table entry for a page that is brought into memory is set as usual, but the page table entry for a page that is not currently in memory is either simply marked invalid or contains the address of the page on disk. This situation is depicted in figure below. Page table when some pages are not in main memory. Notice that making a page invalid will have no effect if the process never attempts to access that page. Hence, if we guess right and page in all pages that are actually needed and only those pages, the process will run exactly as though we had brought in all pages. While the process executes and accesses pages that are memory resident, execution proceeds normally. But what happens if the process tries to access a page that was not brought into memory? Access to a page marked invalid causes a page fault. The paging hardware, in translating the address through the page table, will notice that the invalid bit is set, causing a trap to the operating system. This trap is a result of the operating system's failure to bring the desired page into memory. The procedure for handling this page fault is straightforward as shown in figure below. Page table when some pages are not in main memory. We check an internal table, usually kept with the process control block, for this process to determine whether the reference was a valid or invalid memory access. If the reference was invalid, we terminate the process. If it was valid but we have not yet brought in that page, we now page it in. We find a free frame by taking one frame from the free frame list, for example. We schedule a disk operation to read the desired page into the newly allocated frame. When the disk read is complete, we modify the internal table kept with the process and the page table to indicate that the page is now in memory. We restart the instruction that was interrupted by the trap. The process can now access the page as though it had always been in memory. In the extreme case, we can start executing a process with no pages in memory. When the operating system sets the instruction pointer to the first instruction of the process, which is on a non-memory resident page, the process immediately faults for the page. After this page is brought into memory, the process continues to execute, faulting as necessary until every page that it needs is in memory. At that point, it can execute with no more faults. This scheme is pure demand paging. Never bring a page into memory until it is required. Theoretically, some programs could access several new pages of memory with each instruction execution, one page for the instruction and many for data, possibly causing multiple page faults per instruction. This situation would result in unacceptable system performance. Fortunately, analysis of running processes shows that this behavior is exceedingly unlikely. Programs tend to have locality of reference, which results in reasonable performance from demand paging. The hardware to support demand paging is the same as the hardware for paging and swapping. Page table. This table has the ability to mark an entry invalid through a valid-invalid bit or a special value of protection bits. Secondary memory. This memory holds those pages that are not present in main memory. The secondary memory is usually a high-speed disk. It is known as a swap device, and the section of disk used for this purpose is known as swap space. A crucial requirement for demand paging is the ability to restart any instruction after a page fault. Because we save the state, registers, condition code, instruction counter of the interrupted process when the page fault occurs, we must be able to restart the process in exactly the same place and state, except that the desired page is now in memory and is accessible. In most cases, this requirement is easy to meet. A page fault may occur at any memory reference. If the page fault occurs on the instruction fetch, we can restart by fetching the instruction again. If a page fault occurs while we are fetching an operand, we must fetch and decode the instruction again and then fetch the operand. As a worst-case example, consider a 3-address instruction such as ADD, the content of A to B, placing the result in C. These are the steps to execute this instruction. 1. Fetch and decode the instruction, ADD. 2. Fetch A. 3. Fetch B. 4. Add A and B. 5. Store the sum in C. If we fault when we try to store in C because C is in a page not currently in memory, we will have to get the desired page, bring it in, correct the page table, and restart the instruction. The restart will require fetching the instruction again, decoding it again, fetching the 2 operands again, and then adding again. However, there is not much repeated work, less than 1 complete instruction, and the repetition is necessary only when a page fault occurs. The major difficulty arises when one instruction may modify several different locations. For example, consider the IBM System 360-370 MVC move character instruction, which can move up to 256 bytes from one location to another, possibly overlapping location. If either block, source or destination straddles a page boundary, a page fault might occur after the move is partially done. In addition, if the source and destination blocks overlap, the source block may have been modified, in which case we cannot simply restart the instruction. This problem can be solved in 2 different ways. In one solution, the microcode computers and attempts to access both ends of both blocks. If a page fault is going to occur, it will happen at this step before anything is modified. The move can then take place. We know that no page fault can occur since all the relevant pages are in memory. The other solution uses temporary registers to hold the values of overwritten locations. If there is a page fault, all the old values are written back into memory before the trap occurs. This action restores memory to its state before the instruction was started so that the instruction can be repeated. This is by no means the only architectural problem resulting from adding paging to an existing architecture to allow demand paging, but it illustrates some of the difficulties involved. Paging is added between the CPU and the memory in a computer system. It should be entirely transparent to the user process. Thus, people often assume that paging can be added to any system. Although this assumption is true for a non-demand paging environment where a page fault represents a fatal error, it is not true where a page fault means only that an additional page must be brought into memory and the process restarted. Demand segmentation. Virtual memory can be implemented via demand paging, demand segmentation. Operating system also uses demand segmentation, which is similar to demand paging. Operating system uses demand segmentation where there is insufficient hardware available to implement demand paging. The segment table has a valid bit to specify if the segment is already in physical memory or not. If a segment is not in physical memory, then segment fault results, which traps to the operating system and brings the needed segment into physical memory, much like a page fault. It allows pages that are often referenced with each other to be brought into memory together. This decreases the number of page faults. Another space server would be to keep some of a segment's page table on disk and swap them into memory when needed. Key points. Used when insufficient hardware to implement demand paging. OS/2 allocates memory in segments which it keeps track of through segment descriptors. Segment descriptor contains a valid bit to indicate whether the segment is currently in memory. If segment is in main memory, access continues. If not in memory, segment fault. Directory implementation. The selection of directory allocation and directory management algorithms significantly affects the efficiency, performance, and reliability of the file system. In this section, we discuss the trade-offs involved in choosing one of these algorithms. Linear list. The simplest method of implementing a directory is to use a linear list of file names with pointers to the data blocks. This method is simple to program but time-consuming to execute. To create a new file, we must first search the directory to be sure that no existing file has the same name. Then we add a new entry at the end of the directory. To delete a file, we search the directory for the named file and then release the space allocated to it. To reuse the directory entry, we can do one of several things. We can make the entry as unused by assigning it a special name such as an all blank name, or by including a used, unused bit in each entry, or we can attach it to a list of free directory entries. A third alternative is to copy the last entry in the directory into the freed location and to decrease the length of the directory. A linked list can also be used to decrease the time required to delete a file. The real disadvantage of a linear list of directory entries is that finding a file requires a linear search. Directory information is used frequently and users will notice if access to it is slow. In fact, many operating systems implement a software cache to store the most recently used directory information. A cache hit avoids the need to constantly reread the information from disk. A sorted list allows a binary search and decreases the average search time. However, the requirement that the list be kept sorted may complicate creating and deleting files, since we may have to move substantial amounts of directory information to maintain a sorted directory. A more sophisticated tree data structure such as balanced tree might help here. An advantage of the sorted list is that a sorted directory listing can be produced without a separate sort step. Hash table. Another data structure used for a file directory is a hash table. Here, a linear list stores the directory entries, but a hash data structure is also used. The hash table takes a value computed from the file name and returns a pointer to the file name to the linear list. Therefore, it can greatly decrease the directory search time. Insertion and deletion are also fairly straightforward, although some provision must be made for collisions, situations in which two file names hash to the same location. The major difficulties with the hash table are its generally fixed size and the dependence of the hash function on that size. For example, assume that we make a linear probing hash table that holds 64 entries. The hash function converts file names into integers from 0 to 63, for instance, by using the remainder of a division by 64. If we later try to create a 65th file, we must enlarge the directory hash table, say, to 128 entries. As a result, we need a new hash function that must map file names to the range 0 to 127, and we must recognize the existing directory entries to reflect their new hash function values. Alternatively, we can use a chained overflow hash table. Each hash entry can be a linked list instead of an individual value, and we can resolve collisions by adding the new entry to the linked list. Lookups may be somewhat slowed because searching for a name might require stepping through a linked list of colliding table entries. Still, this method is likely to be much faster than a linear search through the entire directory. Directory structure. Next, we consider how to store files. Certainly, no general-purpose computer stores just one file. There are typically thousands, millions, and even billions of files within a computer. Files are stored on random access storage devices, including hard disks, optical disks, and solid-state memory-based disks. A storage device can be used in its entirety for a file system. It can also be subdivided for finer-grained control. For example, a disk can be partitioned into quarters and each quarter can hold a separate file system. Storage devices can also be collected together into RAID sets that provide protection from the failure of a single disk. Sometimes disks are subdivided and also collected into RAID sets. Partitioning is useful for limiting the sizes of individual file systems, putting multiple file system types on the same device, or leaving part of the device available for other uses such as swap space or unformatted raw disk space. A file system can be created on each of these parts of the disk. An entity containing a file system is generally known as a volume. The volume may be a subset of a device, a whole device, or multiple devices linked together into a RAID set. Each volume can be thought of as a virtual disk. Volumes can also store multiple operating systems, allowing a system to boot and run more than one operating system. Each volume that contains a file system must also contain information about the files in the system. This information is kept in entries in a device directory or volume table of contents. The device directory, more commonly known simply as the directory, record information such as name, location, size, and type for all files on that volume. Storage structure. As we have just seen, a general-purpose computer system has multiple storage devices, and those devices can be sliced up into volumes that hold file systems. Computer systems may have 0 or more file systems, and the file systems may be of varying types. For example, a typical Solaris system may have dozens of file systems of a dozen different types, as shown in the file system list in figure below. We consider only general-purpose file systems, It is worth noting, though, that there are many special-purpose file systems. Consider the types of file systems in the Solaris example mentioned above. TMPFS, a temporary file system that is created in volatile main memory and has its contents erased if the system reboots or crashes. OBJFS, a virtual file system, essentially an interface to the kernel that looks like a file system, that gives debuggers access to kernel symbols. CTFS, a virtual file system that maintains contract information to manage which processes start when the system boots and must continue to run during operation. LOFS, a loop-back file system that allows one file system to be accessed in place of another one. PROCFS, a virtual file system that presents information on all processes as a file system. UFS, ZFS, general-purpose file systems. The file systems of computers, then, can be extensive. Even within a file system, it is useful to segregate files into groups and manage and act on those groups. This organization involves the use of directories. In the remainder of this section, we explore the topic of directory structure. Directories viewed. The directory can be viewed as a symbol table that translates file names into their directory entries. If we take such a view, we see that the directory itself can be organized in many ways. The organization must allow us to insert entries, to delete entries, to search for a named entry, and to list all the entries in the directory. In this section, we examine several schemes for defining the logical structure of the directory system. When considering a particular directory structure, we need to keep in mind the operations that are to be performed on a directory. Search for a file. We need to be able to search a directory structure to find the entry for a particular file. Since files have symbolic names and similar names may indicate a relationship among files, we may want to be able to find all files whose names match a particular pattern. Create a file. New files need to be created and added to the directory. Delete a file. When a file is no longer needed, we want to be able to remove it from the directory. List a directory. We need to be able to list the files in a directory and the contents of the directory entry for each file in the list. Rename a file. Because the name of a file represents its contents to its users, we must be able to change the name when the contents or use of the file changes. Renaming a file may also allow its position within the directory structure to be changed. Traverse the file system. We may wish to access every directory and every file within a directory structure. For reliability, it is a good idea to save the contents and structure of the entire file system at regular intervals. Often, we do this by copying all files to a magnetic tape. This technique provides a backup copy in case of system failure. In addition, if a file is no longer in use, the file can be copied to tape and the disk space of that file released for reuse by another file. In the following sections, we describe the most common schemes for defining the logical structure of a directory. Single-level directory. The simplest directory structure is the simple-level directory. All files are contained in the same directory, which is easy to support and understand. Figure shows single-level directory. A single-level directory has significant limitations, however, when the number of files increases or when the system has more than one user. Since all files are in the same directory, they must have unique names. If two users call their data file test.txt, then the unique name rule is violated. For example, in one programming class, 23 students called the program for their second assignment prog2.c. Another 11 called it assign2.c. Fortunately, most file systems support file names of up to 255 characters, so it is relatively easy to select unique file names. Even a single user on a single level directory may find it difficult to remember the names of all the files as the number of files increases. It is not uncommon for a user to have hundreds of files on one computer system and an equal number of additional files on another system. Keeping track of so many files is a daunting task. Two-level directory. As we have seen, a single-level directory often leads to confusion of file names among the different users. The standard solution is to create a separate directory for each user. In the two-level directory structure, each user has his own user file directory, UFD. The UFDs have similar structures, but each lists only the files of a single user. When a user job starts or a user logs in, the system's master file directory MFD is searched. The MFD is indexed by username or account number, and each entry points to the UFD for that user. Figure shows two-level directory. When a user refers to a particular file, only his own UFD is searched. Thus, different users may have files with the same name as long as all the file names within each UFD are unique. To create a file for a user, the operating system searches only that user's UFD to ascertain whether another file of that name exists. To delete a file, the operating system confines its search to the local UFD. Thus, it cannot accidentally delete another user's file that has the same name. The user directories themselves must be created and deleted as necessary. A special system program is run with the appropriate username and account information. The program creates a new UFD and adds an entry for it to the MFD. The execution of this program might be restricted to system administrators. The allocation of disk space for user directories can be handled with the techniques for files themselves. Although the two-level directory structure solves the name collision problem, it still has its disadvantages. This structure effectively isolates one user from another. Isolation is an advantage when the users are completely independent, but is a disadvantage when the users want to cooperate on some task and to access one another's files. Some systems simply do not allow local user files to be accessed by other users. Directory structure. If access is to be permitted, one user must have the ability to rename a file in another user's directory. To name a particular file uniquely in a two-level directory, we must give both the user name and the file name. A two-level directory can be thought of as a tree or an inverted tree of height 2. The root of the tree is the MFD. Its direct descendants are the UFDs. The descendants of the UFDs are the files themselves. The files are the leaves of the tree. Specifying a username and a file name defines a path in the tree from the root, the MFD, to a leaf, the specified file. Thus, a username and a file name define a path name. Every file in the system has a path name. To name a file uniquely, a user must know the path name of the file desired. For example, if user A wishes to access her own test file named test.txt, she can simply refer to test.txt. To access the file name test.txt of user B with directory entry name user B, however, she might have to refer to /user B /test.txt. Every system has its own syntax for naming files and directories other than the user's own. Additional syntax is needed to specify the volume of a file. For instance, in Windows, a volume is specified by a letter followed by a colon. Thus, a file specification might be C:/userb/test. Some systems go even further and separate the volume, directory name, and file name parts of the specification. In VMS, for instance, the file login.com might be specified as open brackets sst.jdeck close brackets login.com /1, where U is the name of the volume, SST is the name of the directory, JDEC is the name of the subdirectory, and 1 is the version number. Other systems such as Unix and Linux simply treat the volume name as part of the directory name. The first name given is that of the volume and the rest is the directory and file. For instance, /pbg/test might specify volume U, directory pbg, and file test. A special instance of this situation occurs with the system files. Programs provided as part of the system, loaders, assemblers, compilers, utility routines, libraries, and so on, are generally defined as files. When the appropriate commands are given to the operating system, these files are read by the loader and executed. Many command interpreters simply treat such a command as the name of a file to load and execute. In the directory system as we defined it above, this file name would be searched for in the current UFD. One solution would be to copy the system files into each UFD. However, copying all the system files would waste an enormous amount of space. If the system files requires 5 MB, then supporting 12 users would require 5 times 12 equals to 60 MB just for copies of the system files. The standard solution is to complicate the search procedure slightly. A special user directory is defined to contain the system files, for example, user 0. Whenever a file name is given to be loaded, the operating system first searches the local UFD. If the file is found, it is used. If it is not found, the system automatically searches the special user directory that contains the system files. The sequence of directories searched when a file is named is called the search path. The search path can be extended to contain an unlimited list of directories to search when a command name is given. This method is the one most used in Unix and Windows. Systems can also be designed so that each user has his own search path. Tree-structured directories. Once we have seen how to view a two-level directory as a two-level tree, the natural generalization is to extend the directory structure to a tree of arbitrary height. Figure shows tree-structured directory structure. This generalization allows users to create their own subdirectories and to organize their files accordingly. A tree is the most common directory structure. The tree has a root directory and every file in the system has a unique path name. A directory or subdirectory contains a set of files or subdirectories. A directory is simply another file, but it is treated in a special way. All directories have the same internal format. One bit in each directory entry defines the entry as a file 0 or as a subdirectory 1. Special system calls are used to create and delete directories. In normal use, each process has a current directory. The current directory should contain most of the files that are of current interest to the process. When reference is made to a file, the current directory is searched. If a file is needed that is not in the current directory, then the user usually must either specify a path name or change the current directory to be the directory holding that file. To change directories, a system call is provided that takes a directory name as a parameter and uses it to redefine the current directory. Thus, the user can change a current directory whenever she wants. From one change directory function system call to the next, or open function system calls search the current directory for the specified file. Note that the search path may or may not contain a special entry that stands for the current directory. The initial current directory of a user's login shell is designated when the user job starts or the user logs in. The operating system searches the accounting file or some other predefined location to find an entry for this user for accounting purposes. In the accounting file is a pointer to or the name of the user's initial directory. This pointer is copied to a local variable for this user that specifies the user's initial current directory. From that shell, other processes can be spawned. The current directory of any subprocess is usually the current directory of the parent when it was spawned. Path names can be of two types, absolute and relative. An absolute path name begins at the root and follows a path down specified file, giving the directory names on the path. A relative path name defines a path from the current directory. For example, in the tree-structured file system in figure above, if the current directory is root/spell/mail, then the relative path name prt/first refers to the same file as does the absolute path name root/spell/mail/prt/first. Allowing a user to define her own subdirectories permits her to impose a structure on her files. This structure might result in separate directories for files associated with different topics. For example, a subdirectory was created to hold the text of this book, or different forms of information. For example, the directory programs may contain source programs. The directory bin may store all the binaries. An interesting policy decision in a tree-structured directory concerns how to handle the deletion of a directory. If a directory is empty, its entry in the directory that contains it can simply be deleted. However, suppose the directory to be deleted is not empty, but contains several files or subdirectories. One of the two approaches can be taken. Some systems will not delete a directory unless it is empty. Thus, to delete a directory, the user must first delete all the files in that directory. If any subdirectories exist, this procedure must be applied recursively to them so that they can be deleted also. This approach can result in a substantial amount of work. An alternative approach, such as that taken by the Unix rm command, is to provide an option. When a request is made to delete a directory, all that directory's files and subdirectories are also to be deleted. Either approach is fairly easy to implement. The choice is one of policy. The latter policy is more convenient, but it is also more dangerous because an entire directory structure can be removed with one command. If that command is used in error, a large number of files and directories will need to be restored, assuming a backup exists. With a tree-structured directory system, users can be allowed to access, in addition to their files, the files of other users. For example, user B can access a file of user A by specifying its path names. User B can specify either an absolute or a relative path name. Alternatively, user B can change her current directory to be user A's directory and access the file by its file names. Acyclic graph directories. Consider two programmers who are working on a joint project. The files associated with that project can be stored in a subdirectory, separating them from other projects and files of the two programmers. But since both programmers are equally responsible for the project, both want the subdirectory to be in their own directories. In this situation, the common subdirectory should be shared. A shared directory or file exists in the file system in two or more places at once. A tree structure prohibits the sharing of files or directories. An acyclic graph, that is, a graph with no cycles, allows directories to share subdirectories and files. Figure shows acyclic graph directory structure. The same file or subdirectory may be in two different directories. The acyclic graph is a natural generalization of the tree-structured directory scheme. It is important to note that a shared file or directory is not the same as two copies of the file. With two copies, each programmer can view the copy rather than the original, but if one programmer changes the file, the changes will not appear in the other's copy. With a shared file, only one actual file exists, so any changes made by one person are immediately visible to the other. Sharing is particularly important for subdirectories. A new file created by one person will automatically appear in all the shared subdirectories. When people are working as a team, all the files they want to share can be put into one directory. The UFD of each team member will contain this directory of shared files as a subdirectory. Even in the case of a single user, the user's file organization may require that some file be placed in different subdirectories. For example, a program written for a particular project should be both in the directory of all programs and in the directory for that project. Shared files and subdirectories can be implemented in several ways. A common way, exemplified by many of the Unix systems, is to create a new directory entry called a link. A link is effectively a pointer to another file or subdirectory. For example, a link may be implemented as an absolute or a relative path name. When a reference to a file is made, we search the directory. If the directory entry is marked as a link, then the name of the real file is included in the link information. We resolve the link by using that path name to locate the real file. Links are easily identified by their format in the directory entry or by having a special type on systems that support types and are effectively indirect pointers. The operating system ignores these links when traversing directory to trees to preserve the acyclic structure of the system. Another common approach to implementing shared files is simply to duplicate all information about them in both sharing directories. Thus, both entries are identical and equal. Consider the difference between this approach and the creation of a link. The link is clearly different from the original directory entry. Thus, the two are not equal. Duplicate directory entries, however, make the original and the copy indistinguishable. A major problem with duplicate directory entries is maintaining consistency when a file is modified. An acyclic graph directory structure is more flexible than a simple tree structure, but it is also more complex. Several problems must be considered carefully. A file may now have multiple absolute path names. Consequently, distinct file names may refer to the same file. This situation is similar to the aliasing problem for programming languages. If we are trying to traverse the entire file system to find a file, to accumulate statistics on all files, or to copy all files to backup storage, this problem becomes significant since we do not want to traverse shared structures more than once. Another problem involves deletion. When can the space allocated to a shared file be delocated or reused? One possibility is to remove the file whenever anyone deletes it, but this action may leave dangling pointers to the now non-existent file. Worse, if the remaining file pointers contain actual disk addresses, then the space is subsequently reused for other files. These dangling pointers may point into the middle of other files. In a system where sharing is implemented by symbolic links, the situation is somewhat easier to handle. The deletion of a link need not affect the original file, only the link is removed. If the file entry itself is deleted, the space for the file is delocated, leaving the links dangling. We can search for these links and remove them as well, but unless a list of the associated links is kept with each file, this search can be expensive. Alternatively, we can leave the links until an attempt is made to use them. At that time, we can determine that the file of the name given by the link does not exist and can fail to resolve the link name. The access is treated just as with any other illegal file name. In this case, the system designer should consider carefully what to do when a file is deleted and another file of the same name is created before a symbolic link to the original file is used. In the case of Unix, symbolic links are left when a file is deleted, and it is up to the user to realize that the original file is gone or has been replaced. Microsoft Windows uses the same approach. Another approach to deletion is to preserve the file until all references to it are deleted. To implement this approach, we must have some mechanism for determining that the last reference to the file has been deleted. We could keep a list of all references to a file, directory entries, or symbolic links. When a link or a copy of the directory entry is established, a new entry is added to the file reference list. When a link or directory is deleted, we remove its entry on the list. The file is deleted when its file reference list is empty. The trouble with this approach is the variable and potentially large size of the file reference list. However, we really do not need to keep the entire list. We need to keep only a count of the number of references. Adding a new link or directory entry increments the reference count. Deleting a link or entry decrements the count. When the count is 0, the file can be deleted. There are no remaining references to it. The Unix operating system uses this approach for non-symbolic links or hard links, keeping a reference count in the file information block or inode. By effectively prohibiting multiple references to directories, we maintain an acyclic graph structure. To avoid problems such as the ones just discussed, some systems simply do not allow shared directories or links. General Graph Directory. A serious problem with using an acyclic graph structure is ensuring that there are no cycles. If we start with a two-level directory and allow users to create subdirectories, a tree-structured directory results. It should be fairly easy to see that simply adding new files and subdirectories to an existing tree-structured directory preserves the tree-structured nature. However, when we add links, the tree structure is destroyed, resulting in a simple graph structure. Figure General Graph Directory. The primary advantage of an acyclic graph is the relative simplicity of the algorithms to traverse the graph and to determine when there are no more references to a file. We want to avoid traversing shared sections of an acyclic graph twice, mainly for performance reasons. If we have just searched a major shared subdirectory for a particular file without finding it, we want to avoid searching that subdirectory again. The second search would be a waste of time. If cycles are allowed to exist in the directory, we likewise want to avoid searching any component twice for reasons of correctness as well as performance. A poorly designed algorithm might result in an infinite loop continually searching through the cycle and never terminating. One solution is to limit arbitrarily the number of directories that will be accessed during a search. A similar problem exists when we are trying to determine when a file can be deleted. With acyclic graph directory structures, a value of 0 in the reference count means that there are no more references to the file or directory and the file can be deleted. However, when cycles exist, the reference count may not be 0 even when it is no longer possible to refer to a directory or file. This anomaly results from the possibility of self-referencing or a cycle in the directory structure. In this case, we generally need to use a garbage collection scheme to determine when the last reference has been deleted and the disk space can be relocated. Garbage collection involves traversing the entire file system, marking everything that can be accessed. Then, a second pass collects everything that is not marked onto a list of free space. A similar marking procedure can be used to ensure that a traversal or search will cover everything in the file system once and only once. Garbage collection for a disk-based file system, however, is extremely time-consuming and is thus seldom attempted. Garbage collection is necessary only because of possible cycles in the graph. Thus, an acyclic graph structure is much easier to work with. The difficulty is to avoid cycles as new links are added to the structure. How do we know when a new link will complete a cycle? There are algorithms to detect cycles in graphs. However, they are computationally expensive, especially when the graph is on disk storage. A simpler algorithm in the special case of directories and links is to bypass links during directory traversal. Cycles are avoided and no extra overhead is incurred. Efficiency and performance. Now that we have discussed various block allocation and directory management options, we can further consider their effect on performance and efficient disk use. Disks tend to represent a major bottleneck in system performance since they are the slowest main computer component. In this section, we discuss a variety of techniques used to improve the efficiency and performance of secondary storage. Efficiency. The efficient use of disk space depends heavily on the disk allocation and directory algorithms in use. For instance, Unix inodes are pre-allocated on a volume. Even an empty disk has a percentage of its space lost to inodes. However, by pre-allocating the inodes and spreading them across the volume, we improve the file system's performance. This improved performance results from the Unix allocation and free space algorithms, which try to keep a file's data blocks near the file's inode block to reduce seek time. As another example, let's reconsider the clustering scheme, which improves file seek and file transfer performance at the cost of internal fragmentation. To reduce this fragmentation, BSD Unix varies the cluster size as a file grows. Large clusters are used where they can be filled, and small clusters are used for small files and the last cluster of a file. The types of data normally kept in a file's directory or inode entry also require consideration. Commonly, a last write date is recorded to supply information to the user and to determine whether the file needs to be backed up. Some systems also keep a last access date so that a user can determine when the file was last read. The result of keeping this information is that whenever the file is read, a field in the directory structure must be written to. That means the block must be read into memory, a section changed, and the block written back out to disk because operations on disk occur only in block or cluster chunks. So anytime a file is opened for reading, its directory entry must be read and written as well. This requirement can be inefficient for frequently accessed files, so we must weigh its benefit against its performance cost when designing a file system. Generally, every data item associated with a file needs to be considered for its effect on efficiency and performance. Consider, for instance, how efficiency is affected by the size of the pointers used to access data. Most systems use either 32-bit or 64-bit pointers throughout the operating system. Using 32-bit pointers limits the size of a file to 232 or 4 GB. Using 64-bit pointers allows very large file sizes, but 64-bit pointers require more space to store. As a result, the allocation and free space management methods, linked lists, indexes, and so on use more disk space. One of the difficulties in choosing a pointer size, or indeed any fixed allocation size within an operating system, is planning for the effects of changing technology. Consider that the IBM PC XT had a 10 MB hard drive and an MS-DOS file system that could support only 32 MB. Each FAT entry was 12 bits, pointing to an 8 KB cluster. As disk capacities increased, larger disks had to be split into 32 MB partitions because the file system could not track blocks beyond 32 MB. As hard disks with capacities of over 100 MB become common, The disk data structures and algorithms in MS-DOS had to be modified to allow larger file systems. Each FAT entry was expanded to 16 bits and later to 32 bits. The initial file size decisions were made for efficiency reasons. However, with the advent of MS-DOS version 4, millions of computer users were inconvenienced when they had to switch to the newer, larger file system. Solaris ZFS file system uses 128-bit pointers, which theoretically should never need to be extended. The minimum mass of a device capable of strong 2128 bytes using atomic level storage would be about 272 trillion kilograms. As another example, consider the evolution of the Solaris operating system. Originally, many data structures were of fixed length allocated at system startup. These structures included the process table and the open file table. When the process table became full, no more processes could be created. When the file table became full, no more files could be opened. The system would fail to provide services to users. Table sizes could be increased only by recompiling the kernel and rebooting the system. With later releases of Solaris, almost all kernel structures were allocated dynamically, eliminating these artificial limits on system performance. Of course, the algorithms that manipulate these tables are more complicated, and the operating system is a little slower because it must dynamically allocate and deallocate table entries, but that price is the usual one for more general functionality. Performance. Even after the basic file system algorithms have been selected, we can still improve performance in several ways. Most disk controllers include local memory to form an onboard cache that is large enough to store entire tracks at a time. Once a seek is performed, the track is read into the disk cache starting at the sector under the disk head reading latency time. The disk controller then transfers any sector requests to the operating system. Once blocks make it from the disk controller into main memory, the operating system may cache the blocks there. Some systems maintain a separate section of main memory for a buffer cache where blocks are kept under the assumption that they will be used again shortly. Other systems cache file data using a page cache. The page cache uses virtual memory techniques to cache file data as pages rather than as file system-oriented blocks. Caching file data using virtual addresses is far more efficient than caching through physical disk blocks, as accesses interface with virtual memory rather than the file system. Several systems including Solaris, Linux, and Windows are page caching to cache both process pages and file data. This is known as unified virtual memory. Some versions of Unix and Linux provide a unified buffer cache. To illustrate the benefits of the unified buffer cache, consider the two alternatives for opening and accessing a file. One approach is to use memory mapping. The second is to use the standard system calls read function and write function. Without a unified buffer cache, we have a situation similar to figure shows input-output without a unified buffer cache. Here, the read function and write function system calls go through the buffer cache. The memory mapping call, however, requires using two caches, the page cache and the buffer cache. A memory mapping proceeds by reading in disk blocks from the file system and storing them in the buffer cache. Because the virtual memory system does not interface with the buffer cache, the contents of the file in the buffer cache must be copied into the page cache. This situation, known as double caching, requires caching file system data twice. Not only does it waste memory, but it also wastes significant CPU and input-output cycles due to the extra data movement within system memory. In addition, inconsistencies between the two caches can result in corrupt files. In contrast, when a unified buffer cache is provided, both memory mapping and the read function and write function system calls use the same page cache. This has the benefit of avoiding double caching and it allows the virtual memory system to manage file system data. The unified buffer cache is shown in figure below. Input-output using a unified buffer cache. Regardless of whether we are caching disk blocks or pages or both, LRU seems a reasonable general-purpose algorithm for block or page replacement. However, the evolution of the Solaris page caching algorithms reveals the difficulty in choosing an algorithm. Solaris allows processors and the page cache to share unused memory. Versions earlier than Solaris 2.5.1 made no distinction between allocating pages to a process and allocating them to the page cache. As a result, a system performing many input-output operations used most of the available memory for caching pages. Because of the high rates of input-output, the page scanner reclaimed pages from processes rather than from the page cache when free memory ran low. Solaris 2.6 and Solaris 7 optionally implemented priority paging, in which the page scanner gives priority to process pages over the page cache. Solaris 8 applied a fixed limit to process pages and the file system page cache, preventing either from forcing the other out of memory. Solaris 9 and 10 again changed the algorithms to maximize memory use and minimize thrashing. Another issue that can affect the performance of input-output is whether writes to the file system occur synchronously or asynchronously. Synchronous writes occur in the order in which the disk subsystem receives them, and the writes are not buffered. Thus, the calling routine must wait for the data to reach the disk drive before it can proceed. In an asynchronous write, the data are stored in the cache and control returns to the caller. Most writes are asynchronous. However, metadata writes, among others, can be synchronous. Operating systems frequently include a flag in the open system call to allow a process to request that writes be performed synchronously. For example, databases use the feature for atomic transactions to assure that data reach stable storage in the required order. Some systems optimize their page cache by using different replacement algorithms depending on the access type of the file. A file being read or written sequentially should not have its pages replaced in LRU order because the most recently used page will be used last or perhaps never again. Instead, sequential access can be optimized by techniques known as free behind and read ahead. Free behind removes a page from the buffer as soon as the next page is requested. The previous pages are not likely to be used again and waste buffer space. With read ahead, a requested page and several subsequent pages are read and cached. These pages are likely to be requested after the current page is processed. Retrieving these data from the disk in one transfer and caching them saves a considerable amount of time. One might think that a track cache on the controller would eliminate the need for read-ahead on a multi-program system. However, because of the high latency and overhead involved in making many small transfers from the track cache to main memory, performing a read-ahead remains beneficial. The page cache, the file system, and the disk drivers have some interesting interactions. When data are written to a disk file, the pages are buffered in the cache and the disk driver sorts its output queue according to the disk address. These two actions allow the disk driver to minimize disk-ahead seeks and to write data at times optimized for disk rotation. Unless synchronous writes are required, a process writing to disk simply writes into the cache and the system asynchronously writes the data to disk when convenient. The user process sees very fast writes. When data are read from a disk file, the block input-output system does some read-ahead. However, writes are much more nearly asynchronous than are reads. Thus, output to the disk through the file system is often faster than is input for large transfers, counter to intuition. File system implementation. The file system provides the mechanism for online storage and access to file contents including data and programs. The file system resides permanently on secondary storage, which is designed to hold a large amount of data permanently. This chapter is primarily concerned with issues surrounding file storage and access on the most common secondary storage medium, the disk. We explore ways to structure file use, to allocate disk space, to recover freed space, to track the locations of data, and to interface other parts of the operating system to secondary storage. Performance issues are considered throughout the chapter. Operating systems implement open function and closed function system calls for processes to request access to file contents. In this section, we delve into the structures and operations used to implement file system operations. Overview. Several on-disk and in-memory structures are used to implement a file system. These structures vary depending on the operating system and the file system, but some general principles apply. On disk, the file system may contain information about how to boot an operating system stored there, the total number of blocks, the number and location of free blocks, the directory structure, and individual files. Many of these structures are detailed throughout the remainder of this chapter. Here, we describe them briefly. A boot control block, per volume, can contain information needed by the system to boot an operating system from that volume. If the disk does not contain an operating system, this block can be empty. It is typically the first block of a volume. In UFS, it is called the boot block. In NTFS, it is the partition boot sector. A volume control block, per volume, contains volume or partition details such as the number of blocks in the partition, the size of the blocks, a free block count and free block pointers, and a free FCB count and FCB pointers. In UFS, this is called a superblock. In NTFS, it is stored in the master file table. A directory structure per file system is used to organize the files. In UFS, this includes file names and associated inode numbers. In NTFS, it is stored in the master file table. A per file FCB contains many details about the file. It has a unique identifier number to allow association with a directory entry. In NTFS, this information is actually stored within the master file table, which uses a relational database structure with a row per file. The in-memory information is used for both file system management and performance improvement via caching. The data are loaded at mount time, updating during file system operations, and discarded at dismount. Several types of structures may be included. An in-memory mount table contains information about each mounted volume. An in-memory directory structure cache holds the directory information of recently accessed directories. For directories at which volumes are mounted, it can contain a pointer to the volume table. The system-wide open file table contains a copy of the FCB of each open file as well as other information. The per process open file table contains a pointer to the appropriate entry in the system-wide open file table as well as other information. Buffers hold the file system blocks when they are being read from the disk or written to disk. To create a new file, an application program calls the logical file system. The logical file system knows the format of the directory structures. To create a new file, it allocates a new FCB. Alternatively, if the file system implementation creates all FCBs at file system creation time, an FCB is allocated from the set of free FCBs. The system then reads the appropriate directory into memory, updates it with the new file name and FCB, and writes it back to the disk. A typical FCB is shown in figure below. Some operating systems, including Unix, treat a directory exactly the same as a file, one with a type field indicating that it is a directory. Other operating systems, including Windows, implement separate system calls for files and directories and treat directories as entities separate from files. Whatever the larger structural issues, the logical file system can call the file organization module to map the directory input-output into disk block numbers, which are passed on to the basic file system and input-output control system. Now that a file has been created, it can be used for input-output. First, though, it must be opened. The open function call passes a file name to the logical file system. The open function system call first searches the system-wide open file table to see if the file is already in use by another process. If it is, a per process open file table entry is created pointing to the existing system-wide open file table. This algorithm can save substantial overhead. If the file is not already open, the directory structure is searched for the given file name. Parts of the directory structure are usually cached in memory to speed directory operations. Once the file is found, the FCB is copied into a system-wide open file table in memory. This table not only stores the FCB, but also tracks the number of processes that have the file open. Next, an entry is made in the per process open file table with a pointer to the entry in the system-wide open file table and some other fields. These other fields may include a pointer to the current location in the file for the text read function or write function operation and the access mode in which the file is open. The open function call returns a pointer to the appropriate entry in the per process file system table. All file operations are then performed via this pointer. The file name may not be part of the open file table as the system has no use for it once the appropriate FCB is located on disk. It could be cached, though, to save time on subsequent opens of the same file. The name given to the entry varies. Unix systems refer to it as a file descriptor. Windows refers to it as a file handle. When a process closes the file, the per process table entry is removed and the system-wide entry's open count is decremented. When all users that have opened the file close it, any updated metadata is copied back to the disk-based directory structure and the system-wide open file table entry is removed. Some systems complicate this scheme further by using the file system as an interface to other system aspects such as networking. For example, in UFS, the system-wide open file table holds the inodes and other information for files and directories. It also holds similar information for network connections and devices. In this way, one mechanism can be used for multiple purposes. The caching aspects of file system structures should not be overlooked. Most systems keep all information about an open file except for its actual data blocks in memory. The BSD Unix system is typical in its use of caches wherever disk input-output can be safe. Its average cache hit rate of 85% shows that these techniques are well worth implementing. The BSD Unix system is described fully in Appendix A. The operating structures of a file system implementation are summarized in Figure. Figure: in-memory file system structures. A. File open. B. File read. File system interface. For most users, the file system is the most visible aspect of an operating system. It provides the mechanism for online storage of and access to both data and programs of the operating system and all the users of the computer system. The file system consists of two distinct parts: a collection of files, each storing related data, and a directory structure which organizes and provides information about all the files in the system. File systems live on devices, which we described in the preceding chapter and will continue to discuss in the following one. In this chapter, we consider the various aspects of files and the major directory structures. We also discuss the semantics of sharing files among multiple processes, users, and computers. Finally, we discuss ways to handle file protection necessary when we have multiple users and we want to control who may access files and how files may be accessed. File concept. Computers can store information on various storage media such as magnetic disks, magnetic tapes, and optical disks. So that the computer system will be convenient to use, the operating system provides a uniform logical view of stored information. The operating system abstracts from the physical properties of its storage devices to define a logical storage unit, the file. Files are mapped by the operating system onto physical devices. These storage devices are usually non-volatile, so the contents are persistent between system reboots. A file is a named collection of related information that is recorded on secondary storage. From a user's perspective, a file is the smallest allotment of logical secondary storage, that is, data cannot be written to secondary storage unless they are within a file. Commonly, files represent programs, both source and object forms, and data. Data files may be numeric, alphabetic, alphanumeric, or binary. Files may be free form, such as text files, or may be formatted rigidly. In general, a file is a sequence of bits, bytes, lines, or records, the meaning of which is defined by the file's creator and user. The concept of a file is thus extremely general. The information in a file is defined by its creator. Many different types of information may be stored in a file. Source or executable programs, numeric or text data, photos, music, video, and so on. A file has a certain defined structure which depends on its type. A text file is a sequence of characters organized into lines and possibly pages. A source file is a sequence of functions, each of which is further organized as declarations followed by executable statements. An executable file is a series of code sections that the loader can bring into memory and execute. File attributes. A file is named for the convenience of its human users and is referred to by its name. A name is usually a string of characters such as example.c. Some systems differentiate between uppercase and lowercase characters in names, whereas other systems do not. When a file is named, it becomes independent of the process, the user, and even the system that created it. For instance, one user might create the file example.c and another user might edit that file by specifying its name. The file's owner might write the file to a USB disk, send it as an email attachment, or copy it across a network, and it could still be called example.c on the destination system. A file's attributes vary from one operating system to another, but typically consist of these. Name. The symbolic file name is the only information kept in human-readable form. Identifier. This unique tag, usually a number, identifies the file within the file system. It is the non-human readable name for the file. Type. This information is needed for systems that support different types of files. Location. This information is a pointer to a device and to the location of the file on that device. Size. The current size of the file in bytes, words, or blocks, and possibly the maximum allowed size are included in this attribute. Protection. Access control information determines who can do reading, writing, executing, and so on. Time, date, and user identification. This information may be kept for creation, last modification, and last use. These data can be useful for protection, security, and usage monitoring. Some newer file systems may also support extended file attributes, including character encoding of the file and security features, such as a file checksum. Figure below illustrates a file info window on Mac OS X which displays a file's attributes. The information about all files is kept in the directory structure, which also resides on secondary storage. Typically, a directory entry consists of the file's name and its unique identifier. The identifier in turn locates the other file attributes. It may take more than a kilobyte to record this information for each file. In a system with many files, the size of the directory itself may be megabytes because directories, like files, must be non-volatile. They must be stored on the device and brought into memory piecemeal as needed. File operations. A file is an abstract data type. To define a file properly, we need to consider the operations that can be performed on files. The operating system can provide system calls to create, write, read, reposition, delete, and truncate files. Let's examine what the operating system must do to perform each of these 6 basic file operations. It should then be easy to see how other similar operations, such as renaming a file, can be implemented. Creating a file. 2 steps are necessary to create a file. First, space in the file system must be found for the file. Second, an entry for the new file must be made in the directory. Writing a file. To write a file, we make a system call specifying both the name of the file and the information to be written to the file. Given the name of the file, the system searches the directory to find the file's location. The system must keep a write pointer to the location in the file where the next write is to take place. The write pointer must be updated whenever a write occurs. Reading a file. To read from a file, we use a system call that specifies the name of the file and where, in memory, the next block of the file should be put. Again, the directory is searched for the associated entry and the system needs to keep a read pointer to the location in the file where the next read is to take place. Once the read has taken place, the read pointer is updated because a process is usually either reading from or writing to a file. The current operation location can be kept as a per process current file position pointer. Both the read and write operations use this same pointer, saving space and reducing system complexity. Repositioning within a file. The directory is searched for the appropriate entry and the current file position pointer is repositioned to a given value. Repositioning within a file need not involve any actual input-output. This file operation is also known as a file seek. Deleting a file. To delete a file, we search the directory for the named file. Having found the associated directory entry, we release all file space so that it can be reused by other files and erase the directory entry. Truncating a file. The user may want to erase the contents of a file but keep its attributes. Rather than forcing the user to delete the file and then recreate it, this function allows all attributes to remain unchanged except for file length, but let the file be reset to length 0 and its file space released. File System Interface. These 6 basic operations comprise the minimal set of required file operations. Other common operations include appending new information to the end of an existing file and renaming an existing file. These primitive operations can then be combined to perform other file operations. For instance, we can create a copy of a file or copying the file to another input-output device, such as a printer or a display, by creating a new file and then reading from the old and writing to the new. We also want to have operations that allow a user to get and set the various attributes of a file. For example, we may want to have operations that allow a user to determine the status of a file, such as the file's length, and to set file attributes such as the file's owner. Most of the file operations mentioned involved searching the directory for the entry associated with the named file. To avoid this constant searching, many systems require that an open function system call be made before a file is first used. The operating system keeps a table called the Open File Table containing information about all open files. When a file operation is requested, the file is specified via an index into this table, so no searching is required. When the file is no longer being actively used, it is closed by the process and the operating system removes its entry from the Open File table. Creates function and delete function are system calls that work with closed rather than open files. Some systems implicitly open a file when the first reference to it is made. The file is automatically closed when the job or program that opened the file terminates. Most systems, however, require that the programmer open a file explicitly with the open function system call before that file can be used. The open function operation takes a file name and searches the directory, copying the directory entry into the open file table. The open function call can also accept access mode information: create, read-only, read-write, append-only, and so on. This mode is checked against the file's permissions. If the request mode is allowed, the file is opened for the process. The open function system call typically returns a pointer to the entry in the open file table. This pointer, not the actual file name, is used in all input-output operations, avoiding any further searching and simplifying the system call interface. The implementation of the open function and close function operations is more complicated in an environment where several processes may open the file simultaneously. This may occur in a system where several different applications open the same file at the same time. Typically, the operating system uses two levels of internal tables: a per-process table and a system-wide table. The per-process table tracks all files that a program has opened. Stored in this table is information regarding the process's use of the file. For instance, the current file pointer for each file is found here. Access rights to the file and accounting information can also be included. Each entry in the per-process table in turn points to a system-wide open file table. The system-wide table contains process-independent information such as the location of the file on disk, access dates, and file size. Once a file has been opened by one process, the system-wide table includes an entry for the file. When another process executes an open function call, a new entry is simply added to the process's open file table, pointing to the appropriate entry in the system-wide table. Typically, the open file table also has an open count associated with each file to indicate how many processes have the file open. Each close function decreases this open count, and when the open count reaches 0, the file is no longer in use and the file's entry is removed from the open file table. In summary, several pieces of information are associated with an open file. File pointer. On systems that do not include a file offset as part of the read function and write function system calls, the system must track the last read-write location as a current file position pointer. This pointer is unique to each process operating on the file and therefore must be kept separate from the on-disk file attributes. File open count. As files are closed, the operating system must reuse its open file table entries, or it could run out of space in the table. Multiple processes may have opened a file, and the system must wait for the last file to close before removing the open file table entry. The file open count tracks the number of opens and closes and reaches 0 on the last close. The system can then remove the entry. Disk location of the file. Most file operations require the system to modify data within the file. The information needed to locate the file on disk is kept in memory so that the system does not have to read it from disk for each operation. Access rights. Each process opens a file in an access mode. This information is stored on the per-process table so the operating system can allow or deny subsequent input-output requests. Some operating systems provide facilities for locking an open file or sections of a file. File locks allow one process to lock a file and prevent other processes from gaining access to it. File locks are useful for files that are shared by several processes, for example, a system log file that can be accessed and modified by a number of processes in the system. File locks provide functionality similar to reader-writer locks. A shared lock is akin to a reader lock in that several processes can acquire the lock concurrently. An exclusive lock behaves like a writer lock. Only one process at a time can acquire such a lock. It is important to note that not all operating systems provide both types of locks. Some systems only provide exclusive file locking. File types. When we design a file system, indeed an entire operating system, we always consider whether the operating system should recognize and support file types. If an operating system recognizes the type of a file, it can then operate on the file in reasonable ways. For example, a common mistake occurs when a user tries to output the binary object form of a program. This attempt normally produces garbage. However, the attempt can succeed if the operating system has been told that the file is a binary object program. A common technique for implementing file types is to include the type as part of the file name. The name is split into two parts, a name and an extension usually separated by a period. Figure shows some common file types. In this way, the user and the operating system can tell from the name alone what the type of file is. Most operating systems allow users to specify a file name as a sequence of characters followed by a period and terminated by an extension made up of additional characters. Examples include resume.docx, server.c, and readerthread.cpp. The system uses the extension to indicate the type of the file and the type of operations that can be done on that file. Only a file with a .com, .exe, or .sh extension can be executed, for instance. The .com and the .exe files are two forms of binary executable files, whereas the .sh file is a shell script containing, in ASCII format, commands to the operating system. Application programs also use the extensions to indicate file types in which they are interested. For example, Java compilers expect source files to have a .java extension, and the Microsoft Word processor expects its files to end with a .doc or .docx extension. These extensions are not always required, so a user may specify a file without the extension to save typing, and the application will look for a file with the given name and the extension it expects. Because these extensions are not supported by the operating system, they can be considered hints to the applications that operate on them. File structure. File types also can be used to indicate the internal structure of the file. A source and object files have structures that match the expectations of the programs that read them. Further, certain files must conform to a required structure that is understood by the operating system. For example, the operating system requires that an executable file have a specific structure so that it can determine where in memory to load the file and what the location of the first instruction is. Some operating systems extend this idea into a set of system-supported file structures with sets of special operations for manipulating files with those structures. This point brings us to one of the disadvantages of having the operating system support multiple file structures. The resulting size of the operating system is cumbersome. If the operating system defines 5 different file structures, it needs to contain the code to support these file structures. In addition, it may be necessary to define every file as one of the file types supported by the operating system. When new applications require information structured in ways not supported by the operating system, severe problems may result. For example, assume that a system supports two types of files: text files composed of ASCII characters separated by a carriage return and line feed, and executable binary files. Now, if we, as users, want to define an encrypted file to protect the contents from being read by unauthorized people, we may find neither file type to be appropriate. The encrypted file is not ASCII text lines, but rather is, apparently, random bits. Although it may appear to be a binary file, it is not executable. As a result, we may have to circumvent or misuse the operating system's file type mechanism or abandon our encryption scheme. Some operating systems impose and support a minimal number of file structures. This approach has been adopted in Unix, Windows, and others. Unix considers each file to be a sequence of 8-bit bytes. No interpretation of these bits is made by the operating system. This scheme provides maximum flexibility but little support. Each application program must include its own code to interpret an input file as to the appropriate structure. However, all operating systems must support at least one structure, that of an executable file, so that the system is able to load and run programs. Internal file structure. Internally, locating an offset within a file can be complicated for the operating system. Disk systems typically have a well-defined block size determined by the size of a sector. All disk input-output is performed in units of one block physical record, and all blocks are the same size. It is unlikely that the physical record size will exactly match the length of the desired logical record. Logical records may even vary in length. Packing a number of logical records into physical blocks is a common solution to this problem. For example, the Unix operating system defines all files to be simply streams of bytes. Each byte is individually addressable by its offset from the beginning or end of the file. In this case, the logical record size is 1 byte. The file system automatically packs and unpacks bytes into physical size blocks, say 512 bytes per block as necessary. The logical record size, physical block size, and packing technique determine how many logical records are in each physical block. The packing can be done either by the user's application program or by the operating system. In either case, the file may be considered a sequence of blocks. All the basic input-output functions operate in terms of blocks. The conversion from logical records to physical blocks is a relatively simple software problem. Because disk space is always allocated in blocks, some portion of the last block of each file is generally wasted. If each block were 512 bytes, for example, then a file of 1949 bytes would be allocated 4 blocks, 2048 bytes. The last 99 bytes would be wasted. The waste incurred to keep everything in units of blocks instead of bytes is internal fragmentation. All file systems suffer from internal fragmentation. The larger the block size, the greater the internal fragmentation. File system structure. Disks provide most of the secondary storage on which file systems are maintained. Two characteristics make them convenient for this purpose. A disk can be rewritten in place. It is possible to read a block from the disk, modify the block, and write it back into the same place. A disk can access directly any block of information it contains. Thus, it is simple to access any file either sequentially or randomly, and switching from one file to another requires only moving the read-write heads and waiting for the disk to rotate. To improve input-output efficiency, input-output transfers between memory and disk are performed in units of blocks. Each block has one or more sectors. Depending on the disk drive, sector size varies from 32 bytes to 4096 bytes. The usual size is 512 bytes. File systems provide efficient and convenient access to the disk by allowing data to be stored, located, and retrieved easily. A file system poses two quite different design problems. The first problem is defining how the file system should look to the user. This task involves defining a file and its attributes, the operations allowed on a file, and the directory structure for organizing files. The second problem is creating algorithms and data structures to map the logical file system onto the physical secondary storage devices. The file system itself is generally composed of many different levels. The structure shown in figure below is an example of a layered design, that is, a layered file system. Each level in the design uses the features of lower levels to create new features for use by higher levels. The input-output control level consists of device drivers and interrupt handlers to transfer information between the main memory and the disk system. A device driver can be thought of as a translator. Its input consists of high-level commands such as retrieve block 123. Its output consists of low-level, hardware-specific instructions that are used by the hardware controller, which interfaces the input-output device to the rest of the system. The device driver usually writes specific bit patterns to special locations in the input-output controller's memory to tell the controller which device location to act on and what actions to take. The basic file system needs only to issue generic commands to the appropriate device driver to read and write physical blocks on the disk. Each physical block is identified by its numeric disk address, for example, drive 1, cylinder 73, track 2, sector 10. This layer also manages the memory buffers and caches that hold various file system, directory, and data blocks. A block in the buffer is allocated before the transfer of a disk block can occur. When the buffer is full, the buffer manager must find more buffer memory or free up buffer space to allow a requested input-output to complete. Caches are used to hold frequently used file system metadata to improve performance, so managing their contents is critical for optimum system performance. The file organization module knows about files and their logical blocks as well as physical blocks. By knowing the type of file allocation used and the location of the file organization module can translate logical block addresses to physical block addresses for the basic file system to transfer. Each file's logical blocks are numbered from 0 or 1 through n. Since the physical blocks containing the data usually do not match the logical numbers, a translation is needed to locate each block. The file organization module also includes the free space manager, which tracks unallocated blocks and provides these blocks to the file organization module when requested. Finally, the logical file system manages metadata information. Metadata includes all of the file system structure except the actual data or contents of the files. The logical file system manages the directory structure to provide the file organization module with the information the latter needs given a symbolic file name. It maintains file structure via file control blocks. A file control block, FCB, an inode in Unix file systems, contains information about the file including ownership, permissions, and location of the file contents. The logical file system is also responsible for protection. When a layered structure is used for file system implementation, duplication of code is minimized. The input-output control and sometimes the basic file system code can be used by multiple file systems. Each file system can then have its own logical file system and file organization modules. Unfortunately, layering can introduce more operating system overhead, which may result in decreased performance. The use of layering, including the decision about how many layers to use and what each layer should do, is a major challenge in designing new systems. Many file systems are in use today, and most operating systems support more than one. For example, most CD-ROMs are written in the ISO 9660 format, a standard format agreed on by CD-ROM manufacturers. In addition to removable media file systems, each operating system has one or more disk-based file systems. Free space management. Since disk space is limited, we need to reuse the space from deleted files for new files, if possible. Write-once optical disks allow only one write to any given sector, and thus reuse is not physically possible. To keep track of free disk space, the system maintains a free space list. The free space list records all free disk blocks, those not allocated to some file or directory. To create a file, we search the free space list for the required amount of space and allocate that space to the new file. The space is then removed from the free space list. When a file is deleted, its disk space is added to the free space list. The free space list, despite its name, may not be implemented as a list, as we discuss next. Bit vector. Frequently, the free space list is implemented as a bitmap or bit vector. Each block is represented by 1 bit. If the block is free, the bit is 1. If the block is allocated, the bit is 0. For example, consider a disk where blocks 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 17, 18, 25, 26, and 27 are free, and the rest of the blocks are allocated. The free space bitmap would be 00, 1111, 00, 111111, 000, 11, 000000, 111, 00000. The main advantage of this approach is its relative simplicity and its efficiency in finding the first free block or n consecutive free blocks on the disk. Indeed, many computers simply bit manipulation instructions that can be used effectively for that purpose. One technique for finding the first free block on a system that uses a bit vector to allocate disk space is to sequentially check each word in the bitmap to see whether that value is not 0, since a 0-valued word contains only 0 bits and represents a set of allocated blocks. The first non-zero word is scanned for the first 1 bit, which is the location of the first free block. The calculation of the block number is number of bits per word times number of 0-value words plus offset of first 1 bit. Again, we see hardware features driving software functionality. Unfortunately, bit vectors are inefficient unless the entire vector is kept in main memory and is written to disk occasionally for recovery needs. Keeping it in main memory is possible for smaller disks but not necessarily for larger ones. A 1.3 GB disk with 512 byte blocks would need a bitmap of over 332 KB to track its free blocks, although clustering the blocks in groups of 4 reduces this number to around 83 KB per disk. A 1 TB disk with a 4 KB blocks requires 256 MB to store its bitmap. Given that disk size constantly increases, the problem with bit vectors will continue to escalate as well. Linked list. Another approach to free space management is to link together all the free disk blocks, keeping a pointer to the first free block in a special location on the disk and caching it in memory. The first block contains a pointer to the next free disk block and so on. Recall our early example in which blocks 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 17, 18, 25, 26 and 27 were free and the rest of the blocks were allocated. In this situation, we would keep a pointer to block 2 as the first free block. Block 2 would contain a pointer to block 3, which would point to block 4, which would point to block 5, which would point to block 8 and so on. Figure linked free space in disk. The scheme is not efficient. To traverse the list, we must read each block, which requires substantial input-output time. Fortunately, however, traversing the free list is not a frequent action. Usually, the operating system simply needs a free block so that it can allocate that block to a file, so the first block in the free list is used. The FAT method incorporates free block accounting into the allocation data structure. No separate method is needed. Grouping. A modification of the free list approach stores the addresses of n free blocks in the first free block. The first n-1 of these blocks are actually free. The last block contains the addresses of another n free blocks and so on. The addresses of a large number of free blocks can now be found quickly, unlike the situation when the standard linked list approach is used. Counting. Another approach takes advantage of the fact that generally several contiguous blocks may be allocated or freed simultaneously, particularly when space is allocated with the contiguous allocation algorithm or through clustering. Thus, rather than keeping a list of n free disk addresses, we can keep the address of the first free block and the number n of free contiguous blocks that follow the first block. Each entry in the free space list then consists of a disk address and a count. Although each entry requires more space than would a simple disk address, the overall list is shorter as long as the count is generally greater than 1. Note that this method of tracking free space is similar to the extent method of allocating blocks. These entries can be stored in a balanced tree rather than a linked list for efficient lookup, insertion and deletion. Space maps. Oracle's ZFS file system, found in Solaris and other operating systems, was designed to encompass huge numbers of files, directories and even file systems. In ZFS, we can create file system hierarchies. On these scales, metadata input-output can have a large performance impact. Consider, for example, that if the free space list is implemented as a bitmap, bitmaps must be modified both when blocks are allocated and when they are freed. Freeing a 1 GB of data on a 1 TB disk could cause thousands of blocks of bitmaps to be updated because those data blocks could be scattered over the entire disk. Clearly, the data structures for such a system could be large and inefficient. In its management of free space, ZFS uses a combination of techniques to control the size of data structures and minimize the input-output needed to manage those structures. First, ZFS creates metaslabs to divide the space on the device into chunks of manageable size. A given volume may contain hundreds of metaslabs. Each metaslab has an associated space map. ZFS uses the counting algorithm to store information about free blocks. Rather than write counting structures to disk, it uses log-structured file system techniques to record them. The space map is a log of all block activity, allocating and freeing, in time order, in counting format. When ZFS decides to allocate or free space from a metaslab, it loads the associated space map into memory in a balanced tree structure for every efficient operation, indexed by offset, and replays the log into that structure. The in-memory space map is then an accurate representation of the allocated and free space in the metaslab. ZFS also condenses the maps as much as possible by combining contiguous free blocks into a single entry. Finally, the free space list is updated on disk as part of the transaction-oriented operations of ZFS. During the collection and sorting phase, block requests can still occur, and ZFS satisfies these requests from the log. In essence, the log plus the balanced tree is the free list. Logical versus physical address space. An address generated by the CPU is commonly referred to as a logical address, whereas an address seen by the memory unit, that is, the one loaded into the memory address register of the memory, is commonly referred to as a physical address. The compile time and load time address binding methods generate identical logical and physical addresses. However, the execution time address binding scheme results in differing logical and physical addresses. In this case, we usually refer to the logical address as a virtual address. We use logical address and virtual address interchangeably in this text. The set of all logical addresses generated by a program is a logical address space. The set of all physical addresses corresponding to these logical addresses is a physical address space. Thus, in the execution time address binding scheme, the logical and physical address spaces differ. The runtime mapping from virtual to physical addresses is done by a hardware device called the Memory Management Unit, MMU. We can choose from many different methods to accomplish such mapping. For the time being, we illustrate this mapping with a simple MMU scheme that is a generalization of the base register scheme. The base register is now called a relocation register. The value in the relocation register is added to every address generated by a user process at the time the address is sent to the memory. See figure below. For example, if the base is at 14,000, that is 14000, then an attempt by the user to address location 0 is dynamically relocated to location 14000, and access to location 346 is mapped to location 14346. The user program never sees the real physical addresses. The program can create a pointer to location 346, store it in memory, manipulate it, and compare it with other addresses, all as the number 346. Only when it is used as a memory address, in an indirect load or store, perhaps, is it relocated relative to the base register. The user program deals with logical addresses. The memory mapping hardware converts logical addresses into physical addresses. The final location of a referenced memory address is not determined until the reference is made. We now have two different types of addresses: logical addresses in the range 0 to max and physical addresses in the range r plus 0 to r plus max for a base value r. The user program generates only logical addresses and thinks that the process runs in locations 0 to max. However, these logical addresses must be mapped to physical addresses before they are used. The concept of a logical address space that is bound to a separate physical address space is central to proper memory management.